Today we're going to look at a very interesting phenomena called pulse splitting. We will use a capacitive feedback amplifier schematic to show how this happens. This circuit is formed by two stages. Input stage. This includes the voltage source VS with its source resistance R1 and input cap C1. Second stage. This is made of a transconductance GM and a parallel R2C2 network. These two stages are connected by a feedback capacitor C. The pulse splitting phenomenon happens especially when this feedback capacitor becomes large. To simplify the derivation of the transfer function, we will define two impedances, Z1 and Z2, each with a low-pass filter response. Z1 has a pole frequency at omega 1, and Z2 has a pole frequency at omega 2. To calculate the transfer function of this circuit, we will use the extra element theory again. The first step is to calculate the reference gain. We remove the feedback capacitor C and derive the transfer function as AREF or AR. As you can see, it is the simple second-order transfer function followed by two low-pass responses of V1 and V2. The next step is to calculate the driving impedance. To do this, we set the input source Vs to 0 by shorting it to ground. Then we insert a test current IT at the original location of the feedback capacitor C. By calculating Vt over It, we get the driving impedance Zd. To calculate the null impedance, we put the input source back and tune the tested current It until the output voltage becomes 0. When it does, the ratio between Vt and It is the null impedance Zn. In this zero Vout condition, two interesting happened. First, there is no current flowing into Z2, so the tested current It equals Gn V1. Second, Vt equals to minus V1. This means the null impedance Vt over It equals to minus 1 over Gn. Now we have the reference gain AR, driving impedance Zd, and null impedance An. We can derive the full transfer function of the feedback circuit. After rearranging some parameters, the transfer function can be rewritten as this. Let's check what happens when C equals to 0. The transfer function degenerates back to its original two-pole existence. However, when C is non-zero, the transfer function can be written as this. We can find the zeros and the poles of the system by setting the numerator and denominator to 0. As we can see, there is a positive 0 at Gn over C after capacitive feedback. For the poles, in the high frequency range, the solution is minus C1C over C1C plus C2C plus C1C2. In the low frequency range, the solution becomes minus 1 over Gn multiplied by R1, R2, and C. As the feedback cap increases, the distance between these two poles grows larger, and the positive 0 gets closer to the orange. This is what we call pulse splitting.